Hello everyone, and welcome back to this series on foundational mathematics. Today we're going to continue our discussion of functions and relations and focus on what is referred to as piecewise functions. In short, piecewise functions are just functions that have different pieces from other different types of functions sort of glued together. Let's start off with probably one of the more familiar examples that you're probably already familiar with to some degree. In particular, let's consider the function absolute value of x. So we already know, or should already know, what the graph of the absolute value function looks like. It will look sort of like a v, right? So if you look at this a little bit more carefully, notice that on the left-hand side, or the left-hand portion of this graph, it is the line y is equal to negative x. So this absolute value function is the curve y is equal to negative x for x is less than 0. And if we look on the right-hand side and sort of extend that downward, notice that that is the curve y is equal to x, but it's only present when x is, for example, greater than 0, and we can also include greater than or equal to 0 since it passes through the origin as well, or you could include it on the blue graph, that's okay too. So in order to represent the absolute value function as what we refer to as a piecewise functional representation, we can write it as follows. So f of x is going to be equal to, so this is going to be, for example, piece 1 of our piecewise function, and this is going to be what we refer to as piece 2 of our piecewise function. So piece 1 is going to be equal to the curve minus x, and this is going to be true for x is less than 0, and then we're going to have positive x for x is greater than or equal to 0. So therefore, these two representations here, so f of x is equal to absolute value of x, and f of x is equal to minus x for x less than 0 and x for x greater than or equal to 0 are corresponding to the same exact function, but this is referred to as the piecewise representation of this function. So now, let's assume that this is the representation of the function that we have, and somebody asks you, for example, what is f of 3 equal to? So keep in mind the inside of the functions are x values, so we need to figure out which x value is associated to that number 3. So we know that 3 is greater than or equal to 0, so we're going to be plugging this into piece number 2. Therefore, f of 3 is going to be equal to the same thing as the number we're inputting, i.e. f of x is equal to x, therefore f of 3 is going to be equal to 3. If somebody asks you, okay, well, what is f of minus 5? Minus 5 is less than 0. Therefore, f of 5 is going to be equal to the minus of our input, so that's going to be equal to positive 5. And f of 0 is going to be equal to what? So 0 is greater than or equal to 0, so we're going to be plugging that into piece number 2. So that's just going to be equal to the input value of our function. There's another function that we can actually easily represent in piecewise form, but this one's going to have infinitely many pieces, and that's going to be the greatest integer function or the floor function, which is represented as so. So in case you looked through our discussion on elementary functions, let's assume that this is x and this is going to be y. The floor function is going to have this type of graph where these are just unit lines with length 1 that sort of span over the rational and irrational numbers between any two consecutive integers, right? So that's 1, that's 2, that's 3, that's minus 1, that's minus 2, that's 1, that's 2, and that's minus 1, and that's minus 2, right? So what we can do is represent this as a bunch of constant functions, right? Because each of these, all of these actually, these are all constant functions. So we should be able to represent the floor function as a piecewise function where our pieces are all constant functions. For example, if we look at from x is equal to 0 to 1, including 0 but not including 1, that's just the function y is equal to 0. This piece is just y is equal to 1, this piece is just y is equal to 2, and so on. And notice that, for example, y is equal to 0 starts at 0, y is equal to 1 starts at 1, and y is equal to 2 starts at 2. So what we can do is we can say, okay, well, g of x is equal to 0 for 0 less than or equal to x is less than 1. It's going to be equal to 1 for 1 less than or equal to x less than 2, 2 for 2 less than or equal to x less than 3, and that's going to be minus 1 for minus 1 less than or equal to x less than 0, 0, minus 2 for minus 2 less than or equal to x less than 0, and that's going to continue infinitely onwards in both of these directions. So we have infinitely many pieces, or you could say in more compact form, for g of x is equal to the floor of x, you can also say that g of x is equal to, we can say, for example, k, for k less than or equal to x less than k plus 1, where k is an integer. And that's sort of a more compactified version of your floor function. Let's actually introduce another function that we have not talked about, and as far as I know this does not have a cute name, but let's assume that h of x has the following graph, and let's see if we can construct a piecewise representation for it. So let's assume that we have this piece here, and a little dot there. And let's assume that this, for example, line is going to be y is equal to x plus 1 for x less than 0. Let's assume that this is going to be the line x minus 1 for x greater than 0. And let's assume that that is, of course, the origin 0, 0. So how would we represent this as a piecewise function? So for example, we have piece 1, piece 2, and piece 3 going in order from left to right. So we can say that, for example, h of x is going to be equal to, so piece 1 is going to be x plus 1 for x less than 0, 0 for x is equal to 0, and x minus 1 for x greater than 0. So notice that a couple things, for example, somebody could ask you, what is h of 0? Keep in mind 0 is equal to 0. Therefore, the output is going to be equal to 0. That's where the closed dot is on the graph. If somebody says, for example, what is h of 3? We know that 3 is bigger than 0. So that means this is going to be 3 minus 1, which is going to be equal to 2. And if somebody asks you what is minus 5 evaluated for h, so clearly minus 5 is less than 0. So this is going to be equal to minus 5 plus 1, which is going to be equal to minus 4. And a couple other things to notice here, especially what's going on around 0. So we know that at exactly 0, we have that the function is equal to 0. If we take, for example, 0 and we add some number really, really small but positive to that 0, we get a number really, really close to minus 1. And if we look slightly to the left of 0, i.e. 0 minus some really small number, notice that we have a number that's really, really close to positive 1. Once you get to single variable calculus, these observations are going to be very, very important. Now let us take a moment and see if we can sketch the graph of a piecewise function where we only know the functional representation of each of the pieces. So notice that we have x minus 1 for x less than negative 2. We have the constant function negative 1 for x equals to negative 2. And we have another linear function minus x minus 2 for x greater than minus 2. And the point of interest where these pieces sort of are going to be glued together is x is equal to minus 2. So the easiest way you can sort of go about this is to sketch each of the pieces where each of the pieces have the entire domain R. So piece 1 is going to be equal to, for example, y is equal to x minus 1. Piece 2 is going to be y is equal to minus 1. And then piece 3 is going to be y is equal to minus x minus 2. So if we sketch these graphs, then we're going to have, for example, x minus 1 is going to be that. Y is equal to minus 1 is going to be equal to this, and minus x minus 2 is going to be equal to this. The next thing we need to figure out is what's going on at the breakpoint x is equal to minus 2. So when x is equal to minus 2, what is going on for this graph? When x is equal to minus 2 for this, what is going on in that graph? And when x is equal to minus 2, what's going on in this graph? So when x is equal to minus 2 in piece number 1, we have minus 2 minus 1, which is going to be equal to minus 3. We have, for example, minus 1 for all x values there. And then we have minus 2, which is the same as 2 minus 2, which is going to be equal to 0. Right? So this y value here is going to be equal to minus 3. And keep in mind this is x is less than 2. So that's going to be an open circle at minus 3. And then we have a closed circle because this x is equal to negative 2. And that's going to be located at minus 1. And then we have another open circle at x is equal to 0. Once you have all of the information for each of your pieces, in particular at the breakpoint, now you can start gluing them together. So let's see if we can sketch the graph of this function f. So we have the x-axis and y-axis here. The only y values of interest are going to be 0, -1, and -3. So 0, -1, and -3. And then we have -1 and -2 there. And the rest is going to be superfluous. We can add more information as we need. So, in particular, let's actually look at this function as well, because obviously we're going to have a y-intercept there. When x is equal to 0, that's going to be equal to -2, which we've already labeled on our axis, so that's okay as well. So, piece 1 is going to have a y value of -3. So when x is equal to -2, y is equal to -3, but it's going to be an open circle. So sort of sketch that there. So that's piece number 1. And then piece number 2 has a y value of -1, but that's just the constant function. And then piece number 3 crosses up here, and that's an open circle. And it's going to cross at -2. Right, so that's the next piece. And this is the graph of f. So obviously, since all x values are accounted for, the domain is going to be all real numbers. Because we have less than -2 on piece 1, equals to -2 on piece 2, and greater than -2 on piece 3, and that covers all of the real numbers. And what would be the range of this function? So obviously we do not have any y values in this particular function, so the range is definitely all going to be non-positive. We do not attain the value of 0 because that's going to be an open circle, but we have all values less than 0 on piece 3, which is of course going to include all of the values that are located in piece 1 and piece 2. So this is going to be equal to -infinity to 0 to be the range. And that's going to be parentheses. And let's look at also the intercepts. If we look at the x-intercept, we do not have any. We get really close to the x-axis, but we do not hit the x-axis via piece 3. And if we look at the y-intercepts, we do have 1, and that's going to be located at 0, -2. And that's the domain, range, x-intercepts, and y-intercepts, and also the graph sketch for this piecewise function. Let's make things a bit more interesting, and let's consider the graph of this piecewise function. In this case, we do not only have constant and linear functions, now we have a couple quadratics, and also an absolute value, and also a constant function, in particular 4 pieces, and there's going to be 2 breakpoints that are going to be of interest to us, x equals -3 and x equals 2. So let's consider what this graph is going to look like, but by focusing on each of the little pieces. So let's start off with piece number 1. So piece number 1 is going to be a parabola. So what does y is equal to? X plus 3, the quantity squared, look like? So that is going to be a parabola shifted to the left 3 units. So that's going to be equal to this graph. And notice that this is going to break off at x is equal to -3, because this is only going to be true for x is less than -3. So let's just keep that in mind. Let's look at piece number 2. So piece number 2 is going to be the absolute value of x. So we should know that the graph of that is going to be equal to the v. And this is only going to be true for -3 less than x is less than 2. So x is less than -3, greater than -3, and x is less than 2. And we're going to have a couple open circles there. So we're going to have an open circle located there. We're going to have an open circle there and an open circle there. Let's look at piece number 3, which is going to be y is equal to 0. So y is equal to 0, we know is just a constant function. And this is going to occur at x is equal to 2. So x is equal to 2 is going to be a closed circle at 2. And then let's look at piece number 4. So piece number 4, this little piece here, so what's that going to look like? So that's shifted to the right 2 units, up 5 units, and upside down. So 1, 2, 1, 2, 3, 4, 5, and that's going to be upside down. Right. So that's the graph of piece number 4, where that height value is 5, that's going to be equal to 2, and that's x is greater than 2, so that's going to be an open circle as well. Once we have each of the pieces considered, then we can consider, for example, all of the details. For example, in terms of y-intercepts, the y-intercepts for this particular curve is going to be equal to the point 0, 0. That's the only x-intercept that we have in this picture for piece 2 at least. Piece 1 doesn't have any x-intercepts because that green circle is open. This is also going to be an x-intercept because that's going to be a closed circle. And we're going to have this x-intercept here, which we can find. And I leave that for you as an exercise to figure out that that is going to be the point 2 plus the square root of 5 comma 0. Right? And in terms of the y-intercepts, y-intercept is going to be that particular point there, and that's the only point because functions can't have more than one y-intercept. So let's glue all these pieces together and all of this information together in order to construct the graph of our function g. All right, so piece number 1 is going to start off at -3, and it's going to be an open circle. So this is piece number 1. And then let's move on to piece number 2. Piece number 2 is going to be our absolute value function. So our absolute value function starts off at 3. And it's going to be an open circle because it's less than on the left-hand side. And that's going to be coming on down. And then we're going to be moving all the way over to 2. And then the next value is going to be the constant function. So this is piece number 2. And then piece number 3 is going to be that lonely little circle point. And then the last piece is going to be starting up here at 5 and then coming down. And that's going to cross at the point 2 plus the square root of 5, comma 0, and go downwards. So let's sort of organize what has going on here. So the domain of this function g. So we have all values less than -3 with piece 1. We do not have x is equal to -3, so we definitely have to include a breakpoint there. We all have all values from -3 to 2 via piece number 2. We have x is equal to 2 from piece number 3, and all values bigger than 2 with piece number 4. So therefore that's just going to be -3 to infinity, or you can also say the set of real numbers take away -3. Either would be perfectly fine. And in terms of the range values, notice that piece number 1 is going to attain all values of +5 and higher, and piece number 4 is going to take all values slightly below +5 and below, and piece number 2 and piece number 3 are subsets of each of those pieces. Therefore, all values of y are attained, which is r, and you can also write -infinity to infinity as well. Let's also mention what the intercepts are. So for the x-intercepts, we have a few. We have this point here, and this point here. So we have 3 x-intercepts. So we have 0, 0. We have 2, 0. And we have 2 plus the square root of 5, comma 0. And for the y-intercepts, we have the origin, 0, 0. And that's the intercepts, domain, range, and graph of that fun little piecewise function. The last thing that I want to mention today in terms of applications of piecewise functions is known as interpolation of discrete data points. Before we get into that, let's introduce another very useful function, and that's called the factorial function, which is defined on a domain of natural numbers only. Just a side note, you can extend this domain into, for example, the positive real numbers or possibly even the entire real numbers, but generally speaking, we're only going to consider the natural numbers here, and we'll consider the extensions later on. So the factorial of a natural number, and hence, keep in mind, in case you don't remember what the set of natural numbers is, it's the set of all numbers 1, 2, 3, 4, and so on. So no 0, no negative integers, no decimals with fractional non-zero part, no irrational numbers, and so on. So we denote the factorial of a natural number via n with a little exclamation bar, and it's going to be the product of n with, again, all natural numbers less than it, with the additional definition of 0 factorial being equal to 1. Now, we add this additional definition here because 0 is not a natural number. 0 would be a whole number that's not natural, right? Unless you change your definitions. But if you multiply 0 with all its preceding naturals less than it, well, there wouldn't be any natural numbers less than it, and 0 factorial would be equal to 0 if we take that definition directly. Now, there are many reasons why we would define 0 factorial to be equal to 1, but we won't get into them there. But later on, you'll see why this is actually a reasonable definition. But in some cases, you may want to redefine it to be 0 or 1/2 or other values, which we'll discuss a little bit later. But we'll just take this as the definition. So let's look at this from the piecewise function. So we're going to consider the function f of n, which is going to be a shorthand version of n factorial. So this is going to be equal to the product of n with all of its natural numbers less than it. So n times n minus 1 times n minus 2 all the way down to the last natural number, which is going to be equal to 1. This is going to be true for all n in the natural numbers. We're going to define it to be equal to 1 for n is equal to 0. And we're going to, at least for the time being, not define it for all n not belonging to the union of n with the number 0, i.e. integers that are negative, the real numbers that are not naturals are 0, and so on. Let's look at a couple examples on how to sort of evaluate factorials for these particular whole numbers. So if I were to ask you what is the value of 3 factorial, that's going to be 3 times 2 times 1, which is going to be equal to 6. If somebody asks you what is 5 factorial, that's going to be equal to 5 times 4 times 3 times 2 times 1, but that's just the same as 3 factorial there. So that's going to be equal to 20 times 6, which is going to be equal to 120. So you can sort of do some shortcuts like that. And if somebody wants to be a little fancy, if somebody asks you what is 89 factorial divided by 87 factorial, what would that be equal to? So how would you find it in an intuitive way? So we would do, for example, 89 times 88 times 87 all the way down to 1. So I'm just going to write that as 87 factorial. And on the bottom, we're going to have 87 times 86 times 85 all the way down to 1. But notice that we have 87 factorial in common here. So we're just going to be left with 89 times 88, which is we know to be equal to 7,832. Right? So those are just some basics of factorial functions. Now, although we have defined the factorial as a piecewise function, you can do a lot more with piecewise functions via interpolation. For example, what if I want to sort of extend the factorial function to values beyond the whole numbers, i.e. I want to give a definition for this. So I want to extend this to something. So what we can do is we can do, for example, a linear interpolation extension of the factorial function. So what would that exactly look like? So if I were to graph the factorial function on its natural domain, so for example 0 factorial is going to be equal to 1, 1 factorial is also going to be equal to 1, and then we have 2 factorial which is going to be equal to 2, and then 3 factorial is going to be equal to 6. Let's draw 6 up there and 2 there. And then, of course, that's going to increase all the way down. But if we were to connect these dots with lines, for example, we were to connect these two with lines, that's obviously going to be the constant function y is equal to 1 for 0 less than x less than or equal to 1. And then, for example, if we look at the next piece, one can find that that's actually the line y is equal to x, which is going to be true for 1 less than or equal to x is less than or equal to 2. And then we have another line here, right, which is a little bit more steeper. I'm just going to sort of fade that out because I don't want to guess where that's going to cross. But one can find that that is the line y is equal to 4x minus 6. And that's going to be true for 2 less than or equal to x is less than 3. And I'll let you sort of figure out why that is actually the equation. So if we were to extend this factorial function via linear interpolations, and let's call this extension, for example, L of x. So we're going to extend, for example, x factorial to this new function L of x. So we're extending the domain whole numbers, and we're going to be extending this to, for example, r greater than or equal to 0 via the following function. So we have the function 1, and this is going to be true for 0 less than or equal to x is less than 1. We have the function x for 1 less than or equal to x is less than 2. And we have 4x minus 6 for 2 less than or equal to x is less than 3. And you can also do for all of the other unit intervals, k less than or equal to x is less than k plus 1, where k is an integer. Right? So if somebody were to ask you via this linear interpolation extension of the factorial function, what would 5 halves factorial be extended to? So this would be extended via this function to L of 5 halves, which of course 5 halves is going to be 2.5 as a decimal, which belongs to the interval 2 to 3. So that's going to be equal to 4 times 5 halves minus 6, which is 4 divided by 2, which is 2 times 5, which is 10, minus 6, which is going to be equal to 4. So 5 halves factorial is extended to 4, which is somewhere along that line, right? So that's 2.5. Right. Of course, this is not the only extension of the factorial function that exists, because notice that this interpolation does have sharp corners, and some people, when they extend functions, they don't like sharp corners. Maybe we can have some smooth corners or other properties that we have. But analytical extensions and their applications, definitely a lot more to discuss, but we need a lot more tools to discuss them in a more deeper fashion. So those are the primary things that you definitely need to know when it comes to piecewise function in terms of how to graph them, how to represent them, how to interpret them, and possibly some things on how to apply them to. So I hope you enjoyed this video, and I'll see you in the next one. Take care.